Hello, good morning everybody. Today we will just continue the last part of the phosphorus bearing molecules which are very important industrially. So, we have seen that if we can have simple phosphorus as P4 and that particular P4 how we can utilize, because we have already seen that this particular process where we get P4 molecules, whether you get a red phosphorus or white phosphorus or some kind of black phosphorus. So, the first part was basically your isolation, and then how we can convert this particular molecule to some other also industrially important molecules, such as simple making of your phosphoric acid. So, today we will just see how we can introduce something related to some bond which we can form, which is nothing but a phosphorus sulfur bond, because the presence of phosphorus is very important industrially as well as pharmaceutically. So, if we can have some more connectivity from phosphorus to sulfur, we can get some more interesting molecule and which we can produce industrially quite easily. So, here also basically this particular conversion along with this goes via the formation of P2O5. That means it is a very simple process of oxidation, that if we have elemental phosphorus in our hand, we can oxidize to some kind of oxidized form of it, and the highest level of oxidation beyond your P2O3 molecule, we get P2O5, that means phosphorus in the +5 oxidation state. That means if the pentavalent phosphorus is present giving you P2O4, and this particular P2O4 when react with or absorption of water molecule giving you the corresponding phosphoric acid molecule. So, similarly now we will see that whether it is possible from same part, that means whether we get it from a particular part which will have a phosphorus sulfur bond, that means corresponding analogous compound which is your P2S5. That can also be very important molecule, because we know that this can also give you the different esters of the corresponding acid. So, we will see now that how we can get this particular one as the corresponding formation of P2S5. How we get that? So, you have the corresponding phosphorus 5 sulfide, we consider it as the corresponding one as the phosphorus 5 sulfide, and in terms of its typical inorganic chemistry, the textbook inorganic chemistry what tells us it as a very interesting molecule, because the shape of the molecule is also very much interesting from your typical inorganic chemistry point of view. It has no relationship with that of your production, industrial production, its application and the uses. But we should know how this particular process of making this molecule is going. That means, as I told you just now, that if you have phosphorus which can be oxidized to P2O5, that means typical oxidation process is taking place, and where the elemental phosphorus which is also a P4 molecule and having a tetrahedral shape, that means the 4 phosphorus atoms are in a space connected through some connectivity link, that means phosphorus link if we consider it, and the geometry of the overall molecule is a tetrahedral molecule. So, during the oxidation what we have seen that it has a similar structure, that is P2S5. If we start simply from the structure, which tells us immediately that whether we can correlate it with that of our P2O5 or the dimeric form of it, which is also the P4O10. So, in this particular molecule, which is again the still 4 phosphorus centers are still present, and we have this particular structure where 2 types of phosphorus sulfur linkages were present, and that we will see afterward that how we can utilize it some useful conversion. So, we have the sulfur as the sulfide ions as the bridging groups, and some of them are the terminal. So, 4 phosphorus groups as the terminal sulfur. We can consider it as a double bonded sulfur or a coordinate bond from phosphorus to sulfur. That means if those sulfur centers are easily available, we can transfer those centers from this molecule to some other molecule, where this particular network involving this particular sulfide bridges, these are all sulfide bridges which are very useful to know also, because in the different sorts of biological molecules where we have the iron, and if we consider that iron sulfur protein molecules, we have this sort of linkages, that means sulfur functioning as a sulfide ion, and that sulfide ion is bridging two metal ion centers. Similarly, for this main group element or the non-metallic part, the phosphorus, we have the same sulfur is present and which is bridging two phosphorus centers. So, simplest way of writing this particular conversion is that P4, or if we can at elevated temperature, that is getting atomized, so we can have the phosphorus atoms, or you can write it as a P4, simple P4. P4 is reacting with sulfur, and those sulfurs are also coming from S8 molecule, because the sulfur, when we talk in terms of the corresponding sulfur, isolation of sulfur and industrially important sulfur production as the sulfur compounds, when we talk in our next few classes, we will be considering sulfur. So, there we will see how we can use this S as S8. So, which is the molecular formula of is at the S8. So, this basically giving you typical sulfide form as P4S10, and it has a huge amount of uses. So, it is used in the manufacture of insecticides. So, 40% of the production of this P4S10 is utilized for making insecticides. So, what are those insecticides basically? So, that can have definitely those are phosphorus bearing compounds as well as sulfur bearing compounds. So, if we have both these two together, we will find there are a large number of applications, and industrially those molecules are also interested, because huge demand in the market also. And from the business point of view also, knowing this particular information, that how you make very quickly, because always we have some intention that how cheaply or how we can produce all these at a very low cost, because most of these things are getting from the natural sources as the rock materials, the phosphatic rocks or the phosphate rocks, what I told you in several cases, that the naturally occurring mineral type of thing or ore type of thing, the phosphate rocks are utilized for making phosphorus, and that particular molecule, if we are able to make it to some insecticides, so the procedures, the processes will be very much helpful in understanding the value added molecules which are functioning as a typical insecticide. Similarly, the lubricating oil additives. So, after 40%, remaining 50% of the production of phosphorus 5 sulfide, or we can consider it also phosphorus pentasulfide, but it is the P2S5 or P4S10 is the lubricating oil additives, and the remaining, that means remaining 10% as the flotation agents. So, these are the applications. We will see also that how this lubricating oil additives can be prepared, how whether we are able to use it directly from the P4S10 molecule, or we can have some other modifications, that we will see. So, that information basically a challenging information to everybody, that whether a phosphorus bearing compound we are putting sulfur in it, now that can be converted to a lubricating oil additive. So, how we make it basically, because I told you as the typical phosphate rock, you can utilize it as a phosphate rock, and that phosphate rock can also be offset from the ferrous phosphide, that Fe2P type of molecule. These are all different types of solid state molecules, and the molecular formula is basically Fe2P. So, like that of burning of this particular phosphorus in presence of elemental sulfur, we get this particular molecule. Similarly, the ferrous phosphide or Fe2P, so this pyrite, we consider it also that pyrite ore. So, Fe2P, when it is burnt in presence of 18 sulfur, so 4 of these will be utilized to react with 18 sulfur, giving us back to that P4S10 molecule. So, when we get this P4S10 molecule as a byproduct, we also produce something which is very useful also, this ferrous sulfide, simple ferrous sulfide molecule, not that iron pyrite rock material or the mineral material, but we will be producing ferrous sulfide. So while making this particular thing, that means the P4S10, we are also producing FeS, the ferrous sulfide, as the byproduct. So if we are very much careful enough that whatever amount of iron present in the molecule while burning with sulfur, we convert it to ferrous sulfide as well as P4S10. So sulfur is reacting both way, with iron centers and with the sulfur centers, giving you that ferrous sulfide, and this phosphorus, the remaining phosphorus present in that particular ore material, is reacting then with that of your sulfide or sulfides, giving you that P4S10. So the procedure of making this particular P4S10 molecule will be cheaper and cheaper if we can take care of the byproduct molecule or the byproduct compound what is forming over here. So if we can take also, that means the production of FeS, if we consider the price of FeS also, the ferrous sulfide cost also, and if we can purify this particular ferrous sulfide, and if we can use that particular ferrous sulfide very easily, then we can subtract the price which will be required for the production of P4S10 minus the production of this particular molecule, which will also be useful, because we know that from our laboratory days, from our school days or college days, we know that these ferrous sulfide which are available in the market as the typical sticks, ferrous sulfide sticks, which are used for the production of H2S, the hydrogen sulfide, because we use Gibbs apparatus, and in the Gibbs apparatus, the bottom part of the Gibbs apparatus, we put these ferrous sulfide sticks, and then we put sulfuric acid to produce H2S gas, the hydrogen sulfide gas, as and when required by opening up the stopcock of the Gibbs apparatus. So this is a very useful molecule, because whenever you require this particular gas in a very small amount, because it is a poisonous gas, basically it can pollute the environment also, but you should be careful enough while handling this in the laboratory fume hood that your stopcock is in your hand, and you open that stopcock, your ferrous sulfide will be reacting with sulfuric acid, producing H2S, and the chamber, it has 3 chambers in the Gibbs apparatus, and one of the chamber is filled with that particular gas, and we are taking away this amount of gas. So when the gas pressure is high, it is just detaching that sulfuric acid level from the ferrous sulfide, and the production of H2S is stopped. So we are not producing the excess amount of H2S when it is not required. So this ferrous sulfide production, so always we should think of about the corresponding production of the byproducts. So a typical reaction also, the 4 of these will be reacting with this also. This is another step basically, because this is the elemental sulfur step, and if we can have this iron phosphide, the ferropyrite ore, with that of your another ore, iron sulfide, that FeS2 ore. So these are very cheaply available starting material, the ore molecules or the ore material. So ores, if we can directly combine them, and direct reaction of these 2 ores, one is phosphide based ore, another is sulfide based ore, and if we heat it, so definitely the temperature, the pressure of the reaction and the reactor is also important. But the interesting thing to know is that what we are handling is, one is the iron phosphide and another is the iron sulfide, to make some compound where you can have the composition of phosphorus and sulfur. So we can take out both these together, that means phosphorus from this ore and sulfur from this ore we can take out, and we can produce P4S10. And along with this also we still can produce ferrous sulfides, and those ferrous sulfides are useful again for making these sticks, or you can make some powder, or you can convert it directly to the ferrous sulfate or ferric sulfate or some alum of the ferric sulfate, or by preparation for the preparation of more salts. So these are the basically avenues where you can utilize this, not only the production of P4S10 but also the production of FeS, and which we get basically from your phosphate rock. So what we see now that this particular process what we are talking about, that now we just moved here from this to your P4S10, which is giving us P2 S5. And our intention is that we should have the lubricating oil additives. So, we will be going for making additives, which additives? The lubricating, machine lubricating, we call in common terminology the mobiles, the mobile oils, which are additives for the lubricating oils. And here you see that you have both phosphorus and you have sulfur. Now we get something which is a typical salt basically, and that salt will be making as RO, twice of this RO, P4S10. So how we make it from this particular system? So you have RO, and this RO, if we can get it from alcohols, so large number of alcohols we can use it from there. That means if your R can be methanol or methyl alcohol, it can be ethanol or ethyl alcohol, or a very long chain alcohol such as some number of N values. So, CN H2N plus 1, the alkyl functions, ethyl, methyl and long chain alkyl functions. So, this particular P2S5 or rather P4S10 will be highly reactive in nature. So, if we just simply react with plus 4 of your ROH, the alcohol, the 4 of that ROH giving us the corresponding species, that means this will be formed. So, we can go there directly, twice of this will be forming, and what else will be forming, because you have the hydrogen over here, and that hydrogen will be taking care here only. So, one will be coming what this particular molecule, and like that of your production of ferrous sulfide, now we are also producing hydrogen sulfide. So, we should take care of this hydrogen sulfide when we go some reaction, that hydrogen sulfide is forming as a byproduct, and it should not be allowed to go in the environment such that it can have the corresponding responsibility that you are polluting the environment. So, we should have a closed chamber of thing, and the gas, whatever gas produced from there, should be taken out in a nozzle or any other mechanism that you can store it somewhere, and you can utilize it for making some other sulfide salts. Because if you put in water and if you add something, that means if you add some metal ions over there, the simplest way of making this Mn plus, where N value is equal to 2, that means you can have the nickel ion, you can have the copper ion, you can have the cadmium ions over here. So, a water sample containing those ions, those bivalent ions, can react with this H2S, giving you the corresponding metallic sulfides. So, what about this particular one? So, this particular one is therefore, what is this? How we write from here? This molecule basically is giving now is a P double bonded S, because we are making it from P2S5. So, P double bonded S is there, and another group is SH, and we have 2 RO groups. So, the modification is such that we are moving from your P4 to your P2S5 or P4S10, then we are putting oxygen over here from the alcohol. So, this particular molecule have phosphorus, has sulfur as well as the oxygen, and this H is there. So, definitely we will be getting something where we get this particular SH as the corresponding sodium or ammonium salts, or sometimes potassium salts. If you use some medium which is alkaline with respect to sodium hydroxide, with respect to potassium hydroxide, so you will also get as the potassium salt or the sodium salt. So sodium salt is there already. So these salts, basically the corresponding sodium salt, ammonium salt or potassium salts, will be soluble in water. So this particular one is not still your additive for your lubricating oil, and this N value, if we consider for this particular purpose, N value is greater than equal to 5, then these are very much useful in nature. So this particular molecule, when if we now allow it to react with directly with not any other metal ion salt but zinc oxide, because zinc oxide, when we will study the zinc oxide or zinc based materials, it is also industrially important, very much useful molecule. So zinc oxide is a white powder material, so it can also be used as a paint material. So when we study zinc oxide, so industrially it is very easy to make, because this particular material, when we go from zinc ore or zinc mineral, making zinc oxide will be cheaper compared to the preparation of zinc sulfate or zinc chloride or zinc acetate. So any metal ion salt will be costlier than your corresponding oxides, carbonates or any other thing which is very close to your material which is present in your rock sample or the ore sample or the mineral sample. So zinc carbonate we know, which is known as calamine. So zinc carbonate, if we heat that particular zinc carbonate, if we allow to remove the carbon dioxide from there, we will be remaining with zinc oxide. Zinc oxide is a very useful one along with your zinc carbonate, which is a calamine one, calamine source, it has a huge application for that. So this particular zinc oxide, once it is forming it in, and we all know that this is basic in nature. So either you use as these corresponding salts, that means sodium salt or the potassium salt or the ammonium salt, or you can use directly the corresponding acid, because H is present already. So this is a sulfur based acid, S minus H plus is there. So we will get something where your life now is little bit complicated. Now what we are bringing zinc into the picture to make these additives, the lubricating oil. So what we will be getting here, that this particular part, as we all know, that if we some donor groups from here and if we have some donor groups from here, they can function as a very good chelating agent, like your free carboxylic acid or the carboxylates. So when we have these carboxylates or the carboxylic acids like that of your free acid, like acetic acid or formic acid or any other acid. So how you get the corresponding one as from here, your zinc oxide. So from zinc carbonate you have converted it to zinc oxide. Now if I ask you how will you prepare zinc acetate from there, what will you do? We just simply react this zinc oxide or zinc carbonate with that of your acetic acid, not your concentrated acetic acid, but a little bit dilute one, which can be your 1:1 concentrated acetic acid, and you put that particular carbonate or oxide. So what will happen if you put powder sample of that, your carbon dioxide effervescence you can see, and the whole material will go into the solution as the corresponding zinc ions. And when you concentrate it on water bath in the laboratory, if you concentrate it and if you allow it for crystallization, you will get the corresponding zinc as the corresponding zinc acetate in your hand. So like that, if we have the acetate, if we can recall the corresponding formula of acetate ion, which is CH3COO minus, similarly this is also PSS minus. So like that of your carboxylate function, that carboxylate function can bind a particular metal ion center at the point, so it is functioning as a bidentate ligand. So this particular thing is also giving you the corresponding formation of a bidentate ligation. So will take this particular one, that means this sulfur and this sulfur. So these two, this sulfur and this sulfur will be your chelating part, fine. So we get this particular one is a very simple way. Similarly, you have this and you have this. When you consider the charge in it, because if you have this removal of this H plus as the proton corresponding acid, if you make that corresponding salt also, so this H plus is going away, remaining with this one minus charge on it. So you have one charge over here for this part, the whole part, because the negative charge, the single negative charge will be delocalized over these two sulfur centers, giving you a bidentate mononegative chelating ligand which can bind or which can hold the zinc center from its two positions. So if the zinc environment like that of our phosphorus environment, what we are talking about earlier, that this particular geometry, the three-dimensional geometry on this phosphorus is tetrahedral. Similarly, this zinc will also be a tetrahedral one, and the formula of the complex which we consider as the metal ion complex is nothing but your S2 P OR whole 2, and 2 unit of these will be there, and since hydrogen ions are going away taking this oxygen, so we will have one molecule of H2O. So that is the formula of the complex. Now you get your additive for lubricating oil. So this particular compound, making of this particular compound, for this is useful for your additive for making this lubricating oil. So this compound, that means this one, along with this formation of the sodium and the potassium salt, this can also be intermediate in manufacturing insecticides. Insecticides. How? Because this can be your intermediate for making this. So how you consider it is that you have a insecticide, and if you want to make it, definitely it will be phosphorus based compound, and that phosphorus based compound, along with that we are supplying sulfur. So this particular function, basically, if we can have like your sulfate or the nitrate, you have the nitrogen along with our oxygen. Similarly, that part of functional group, that means you have the phosphorus in your hand and you have the corresponding one as the corresponding sulfur in it, and if you have a typical organic backbone, so that particular molecule can be useful for making this insecticide. So what can be your starting material for this? So definitely your P4S10 will be the starting material for the inorganic chemical, which will be useful for making your insecticide molecule. So stepwise what we are going from one step to the further. So the process is not so difficult, because when we go for the industrial processes, you should know the corresponding one for your temperature, the raw materials, and how we can utilize these things. But always we should keep in our mind that what reaction we are following. If we can have intention to make some phosphorus based compounds, okay, it's fine. Then if we can go for oxidation based on oxygen or the sulfur, we make the corresponding compound. And if we further allow it to some organic part, because this is a very simple example where we are allowing to react this particular P4S10 molecule with alcohol. So any alcohol based molecule, so you can have a very long chain alcohol also. So that long chain alcohol can be modified with the introduction of this particular part. That means if you can have two adjacent oxygen centers from the alcohol part, you can clip it with that pH2 minus unit. So it's basically clipping of this particular two part with that pH2 unit, giving some very useful molecule in your hand. So that we will see also when we talk in terms of the corresponding sulfur compounds, how we can utilize the corresponding sulfate molecules or the sulfuric acid, also putting the sulfate in at the long chain of the corresponding alcohols or any other organic molecule. Okay, thank you very much.